Hello students, let us discuss the terms relaxation time, logarithmic decrement and quality factor for underdamped oscillators. So we take firstly relaxation time. It is the time interval during which the amplitude of the underdamped oscillator decays to 1 over e times of its initial value. The behavior of underdamped oscillator can be shown by diagram. This side we plot time and this side displacement, and the behavior of underdamped oscillator is like this. This diagram shows that the amplitude continuously decays with the passage of time. So in such case, if we take that at a certain time t, the amplitude, this amplitude of the underdamped oscillator is, let us say, A, and after certain time, which is we denote as tau, after certain time tau, the amplitude decays to 1 over e times, which we are saying here, 1 over e times of the initial value. So let us say after time tau, this is, let us say, time tau, and this is the amplitude A prime, which decays to 1 over e times. Then we can very easily find the relaxation time, because we know that the displacement for an underdamped oscillator is given by x is equal to a naught e minus bt into cosine of omega t minus phi. So that is the displacement. But if we talk about amplitude of the displacement, then this is only the amplitude. Therefore, at a certain time, we can take this amplitude is equal to a naught e minus bt. And after time t, this is amplitude at time t, we have substitute time here. And after time t plus this tau, the amplitude will be a prime, which we will show a naught e minus b t plus tau here, because time up to here is t plus tau. Now according to definition, this amplitude after certain time tau will be equal to 1 over e times of its original value. This is the original value at time t. So if it is so, what we can do is we can substitute the values from here. We get e naught, from value of a naught is a prime is a naught e minus bt plus tau is equal to 1 over e times the value of original amplitude, that is a naught e minus bt. Okay, now here a naught will cancel out, and we can write the equation. This equation can be written as e minus bt into e minus b tau. We have splitted the terms here, is equal to, this e is in the denominator, we can take it to the numerator. It becomes e minus 1 into e minus bt. Now e minus bt is on both sides, so this term cancels. We left with it implies e minus b tau is equal to e minus 1. Now comparing the powers both sides, we get minus b tau is equal to minus 1, which gives us b tau is equal to 1. And we have to find what is the relaxation time, that is tau. It implies that tau is equal to 1 over b. And we know that in this equation, when we have derived the displacement, we have substituted the damping force, which we can just revise here. That damping force Fd was directly proportional to velocity dx by dt, and we have taken Fd is equal to r dx by dt, and r over m, we know that r over m was substituted as 2b. It means b is equal to r over 2m. So from here you can say, from here we can write here tau is equal to nothing but 2m over r. So ultimately we get the relaxation time is 2m over r for a underdamped mechanical oscillator in which mass m is attached with the oscillator and r is here damping factor. Now higher the damping factor, lesser will be the relaxation time, and if damping is high, then relaxation time will be small. So the this is the meaning of relaxation time, and this relaxation time is about this we can find where the amplitude falls to around about 36.8% of original value, because we know that E is equal to 2.718 and its reciprocal 1 over E is 0.368. So we have taken that 0.368, that means the value of time when amplitude falls to 0.368 times A, that is the value of that time will be relaxation time. Okay, now let us discuss about logarithmic decrement. Logarithmic decrement is defined as the natural log of the ratio of the amplitude of oscillations of underdamped oscillator to the amplitude one time period after it. So that is the definition. Means you have to take the amplitude at certain time. You can take amplitude at certain time, that you can take t, and divided by the amplitude one time period after it. It means we have seen that the oscillations of underdamped oscillations are shown like this: time along x-axis and displacement along y-axis. Now let us assume at certain time t, here a is the amplitude, and after one time period, that means from here it time period completes here. So after one time period, let us say its amplitude is a prime. Okay, so that is the amplitude at after one time period t. That means this time will be taken as t plus capital T. Now according to definition, this logarithmic decrement, which is denoted by delta, it is given by delta is equal to natural log base e of what? That the amplitude at any certain time, that is, let us say a, divided by amplitude after one time period. That means this is a prime. So it will give you the logarithmic decrement. Let us substitute the values. We get log base e into a. We have to put the value of a, and we know that amplitude for underdamped oscillator, that is given by A is equal to A naught E minus BT, where B is the damping factor. So we can write log E base A naught E minus BT divided by, now in the denominator you have to put amplitude at time t plus tau, therefore we'll write E naught E minus B, time will be t plus capital T. Now solving, we get delta is equal to A cancels, and we can write log of E of E minus BT in the numerator, and in denominator we can split the terms E minus BT into E minus B capital T. So E minus BT cancels and we get log of E into 1 over E minus BT. We take this negative term, that is E minus BT, to the numerator. We get delta is equal to log base E BT, because this negative becomes positive here. Now log and exponential will cancel each other, therefore we get BT, and here delta comes out to be B into T, and we know that B is, we have already studied that B is equal to, B is given by R over 2M into T. So that is the value of logarithmic decrement R over 2M into T. It shows that higher the value of damping factor, higher will be the relaxation time. So this is logarithmic decrement for mechanical underdamped oscillator. And third thing now we have to do, that is quality factor. The quality factor for mechanical underdamped oscillator is defined as that it is the number equal to 2 pi times the ratio of the instantaneous energy of the oscillator to the energy lost during one period after that instant, which means that we have to take the ratio of energy of the oscillator at certain time, instantaneous mean at certain time, and to the energy lost, here the word is lost, energy lost during one period after that instant. It means energy lost means we have to find the change in energy in next one period. So how we can find? We can write this, write it as Q, and Q is equal to, according to this definition, we write 2 pi times the ratio of energy. We define energy, we describe energy with the U, divided by the loss of energy. Loss of energy means change of energy, change in energy means du, and negative sign will show the loss, because positive mean increase, negative mean decrease. So decrease of energy in the next one period mean one time period after that. So that is how we can write the formula for quality factor. Now we have to derive the expression for this, and we know that at a particular time or at a particular instant you can take, let us say this is the diagram of oscillations of underdamped oscillator. At a particular instant of time, let us say this is at time t, we take this as the amplitude, And after one time period, you can take after this, that is t plus capital T, the amplitude is, let us say, A prime. But we don't need amplitude here, we need the energy. And the energy of the oscillator is, that is directly proportional to square of the amplitude. This is how we define energy. It is square of the amplitude. So amplitude, where amplitude of underdamped oscillator A is given by A naught E minus BT. It means square of A square will be A naught square E minus 2BT. And using this, we can write the energy will be equal to A naught square E minus 2BT. So this energy we will place here, but in the denominator we need the change in energy in one time period. So we know that we can find energy by finding differentiation of it, that is du with respect to time will be equal to the, we have to find differentiation, that is A naught square, that is constant, minus 2b will be multiplied here into E minus 2bt, exponential term will remain same. But since we have to take this in the next one period, therefore what we can write is that du will be equal to A naught square minus term here 2 into b E minus 2bt, and we can multiply this dt to this side. And this time period will be change in time, that is now time period which is changed, that is one time period. Therefore dt can be where dt can be placed as capital T. So what we get is, in this case we can put this t and we have to find loss of it, that means minus du will give you minus of this, minus minus will cancel, therefore we get 2b A naught square E minus 2bt multiplied by capital T. So this is du. Now we have got minus du and we have u here. Let us put the values and we get q is equal to, we have minus du is equal to the value of minus du we have to put here. So 2 pi times value of u we will put here, which is this is A naught square E minus 2bt divided by this value, that is du. It is 2b A naught square E minus 2bt into t. So you see this term, exponential term will cancel and A naught square also cancels. We left with only 1 over 2bt multiply by 2 pi. So you can write 2 pi here. So ultimately what we get is that it gives you q quality factor comes out to be now 2 cancels pi over bt, but b is equal to r over 2m. Therefore we can get q is equal to this, r will come here, so 2 pi m over rt. So 2 pi m over rt, this is the value of, we can quality factor, 2 pi m over rt is the quality factor for mechanical underdamped oscillator. So this way we had defined all the three values, we have learned all the three terms. One is relaxation time, logarithmic decrement and quality factor. for underdamped oscillator.